along those lines, we're going to see that the air really changes temperatures. It's like I'll change temperature right now. How about water? Does it change temperature very quickly? No. So, and soil is somewhere kind of in between. So we have a cooling effect with clouds during the daytime. And then have you noticed this? So this is my nighttime. We'll draw the kind of a crescent moon, try to anyway. Oh my goodness, looks like it is a bad moon. Looks like a banana. Yes, it does look like a banana. And I don't know what that is, but so let's go ahead and draw in clouds again. Green clouds, that's kind of strange. But one of the things we've talked about, and you tell me what this is, so that's the Earth's surface. So I'll pick red on purpose. So what is this?
Well, the Earth's trying to push its radiation back up.
Exactly. This is the Earth, we say re-radiating. Okay, if it's re-radiating, where did it get it from the first place? From the sun, exactly, during the day, exactly. So honestly, in this case, at night, we definitely, I kind of say that the clouds can act as a blanket at nighttime. You know,
so during the summer when we have clouds at night, the temperature doesn't drop.
That's right, that's right. During the summertime, she was saying if you have clouds, you don't get that cooling effect as you turn away from the sun. Yeah.
Sometimes during summer without the clouds, during night, it's still pretty
Balmy.
warm out.
And you know what, that points out, and I've been thinking about this, that points out a good point that sometimes it's like, we're going to talk about air masses. And air masses are like the state of Missouri, 2 Missouris, okay, air masses are humongous. So actually we can have a chunk of air that has kind of moved in, okay, from, if it's warm, kind of from the south, a chunk of air that's moved in, or if it's a cooler chunk of air from the north, okay, and that actually can kind of throw off or set the design or whatever for what our temperatures are going to be. Or it could be a day-night thing. So we kind of have a couple factors going on. Yes. Okay. Greenhouses. Anybody ever worked in a greenhouse? Really? Oh, cool. You've been through one? The only ones I've been through, yeah, from like Lowe's or something like that, where they try to have clear, ceilings and stuff and let the light in. And can it get hot in the greenhouse? Okay. Cool. Well, what they have in common is basically they'll let in energy. And that yellow or kind of orange there is the energy it's letting in. We talked about how energies, and in this case this is called shortwave energy, shortwave radiation. That energy goes through the glass, but it interacts with the stuff in the greenhouse, plants or the floor or whatever, and actually it is converted into what we call the red things, which are long wave radiation. Short wave radiation, long wave radiation. And here's the deal. Although your glass, your plastic says, short wave, you're fine, come on through. When it comes time for now that different type of energy, which is now long wave radiation, it's like, stay where you are. Yep, time out, stay where you are.
So it condenses on the glass?
So it's blocked by the glass and it kind of bounces around. The heat just stays trapped. Okay, now it can kind of ooze a little bit, but it doesn't go straight through like the short wave came straight through and the long wave. It's like, nope, you're staying here. Yeah.
Stay.
Yes, stay, exactly. Okay.
Because that kind of helps with, say, if your house is cold in the morning, but when the sun hits it directly, and you have plastic up during the winter,
Yep.
and it stays warm, it's like,
Yeah, exactly. You have the plastic up, and if the sun can shine through your glass and your plastic, it's in your house, man. It can be nice and warm. Yeah, it can stay nice and warm.
yeah, where I live, that basically in the morning, the sun really doesn't hit the side of the house, but when it sets, full blast.
Come on through. So this is called the greenhouse effect. And of course, you've heard of the greenhouse effect for the planet, right? So that's why I'm going to switch gears. But all it is basically short wave can come through, okay, but long wave cannot. And so this is how it's likened to the Earth, okay, the greenhouse effect on the Earth. So again, you see those short wave radiation. So remember what the short wave means. We talked about energy, those cousins that have different wavelengths. Short wave is the short wavelengths. So basically visible light and shorter is the way I think of it. Okay, if you look at what's shorter than visible light?
X-ray, gamma ray, UV.
X-ray, gamma ray, and UV. UV jumps right next to it, exactly. Those things can come right through if they make it. Okay, so, but what happens to the Earth when the sun shines on it? The geosphere.
Warms up.
It warms up, exactly. And so what you see on the next one is the warming up part. Maybe. Oop. Okay. So you see that, I call that re-radiation, okay? I'm going to probably add a few terms to that. You're going to hear me call it different things, but it's all the same thing. It's basically the Earth is warm, it's oozing, it's radiating that thermal energy. And you see it interacting with some of the gas particles. Okay, here's a question. How many people, and I'm going to ask you, is it a variable gas or a permanent gas? Is carbon dioxide, how many people think carbon dioxide is a variable gas? Me too, it is a variable gas. Why is it a variable gas?
Because the levels are different.
Because the levels are different. Yep. So variable and permanent. How many people think water is a variable gas? Water is a variable gas. It's permanently in the atmosphere, but it varies by its concentration. Yep, that's what variable means.
Kind of confusing.
It is kind of confusing. So the last one then shows the interaction of those gas particles with that heat energy. Okay, so heat energy coming from the Earth, and this is saying, those gas particles saying, heat energy, you're staying here. They're kind of like the glass pane in a greenhouse. Okay, or plastic there.
So they're keeping that?
They keep it in. Yep. But not all planets have an atmosphere, and not all planets have something that acts as a greenhouse gas. So that's why we call carbon dioxide and water vapor. Water vapor is a greenhouse gas. Why? Because it acts like that. It traps long wave radiation or heat. Same thing. Yep. So, I have some comparisons. That is the Earth, and this is the Moon. What's the difference? What's the Moon? What's different?
It doesn't have an atmosphere to hold the
Right.
heat
The Moon doesn't have an atmosphere. So basically, the Moon's surface does get warm. You've got it, right?
Till night.
Right, that's right. The nighttime side of the Moon is pretty chilly.
in. Dark side of the moon.
Yeah, exactly. Okay, I don't know if you're familiar with the planet Venus's situation. Okay, the thing about Venus is if we were to look at it, instead of being, let's see, our atmosphere is like 80-20 nitrogen, oxygen. Venus is a large percent of it is carbon dioxide. So we're only trace carbon dioxide. They have a lot of carbon dioxide.
So we can't live on the planet.
Venus would be problematic.
It's too
Yeah,
hot.
it'd be hard to terraform. Yeah, it's very hot.
Yeah, because
Mars are coming linking to the next planet. Doesn't use this one.
If you were going to choose a planet to go land on and kind of make it yours, I'd pick Mars. Yeah, Venus has what we call, sometimes they've called it a runaway greenhouse. Okay, so basically, yeah, it's got a lot of carbon dioxide. So anything that the sun sends, it's like, hey, it stays. And its daytime and nighttime temperatures are about the same because it has a nice thick blanket. It does have clouds though, so we talked about how clouds have a cooling effect. I don't know, but
they also have a warming effect. So
yeah, they can have a warming effect during the night.
You know what we should do with Venus? Just put like a plant on there, see if it lives.
What's that?
Put a plant or something.
Oh yeah,
See if it lives.
yeah, random, yeah.
Just a random object.
Yeah, I kill plants, maybe they would live on Venus.
plants too. Maybe
So-
not concrete, though.
But the problem, we talk about visiting Venus and such.
It's too hot.
It is too hot, and so when you think about water being, water will boil at 100 degrees, right, Celsius or 212 Fahrenheit. I mean, water can't be an ongoing liquid on.
Right. Okay.
So I know. So this is a really busy slide. I'll warn you, it's just kind of an overview. I'm not going to ask you these specific numbers, but these are things that we've some that we've talked about. If you think of basically at random 100 units coming from the sun, something's got to happen with those 100 units. You know, energy cannot be destroyed, right? Well, yep. Some of it doesn't make it to the Earth, doesn't make it into the atmosphere or to the Earth's surface. About 30 units, you know, just typical. Okay. The clouds are a player. In this scenario, you can kind of see that the clouds are interacting with some of that incoming energy. Let's say 20 units are absorbed by the clouds. Okay. And let's go ahead and say the clouds are kind of spotty. So actually, 50 units makes it to the geosphere and goes ahead and heats up, okay, the Earth's surface. Then actually, the Earth, we talked about relocating heat by convection, conduction, and radiation, actually. So kind of convection, thermal energy, we talked about, convective lifting. Let's say 7 of those 50 units go up that way. Okay, and those units actually then can be absorbed by the atmosphere. Let's say 23 units of energy are lost because they're used up by taking water from a liquid to a gas. It takes water to evaporate our oceans. Water. It takes energy to evaporate the liquid in our oceans. Let's say 23 units do that. Okay, and let's just say oozing the energy we've been talking about, that long wave radiation. Let's say that 114 units are kind of wiggled out, but actually kind of got 94 units from the atmosphere. So basically 20 units wiggle out. Actually, if you add those 3 terms along the bottom, you surprisingly, or maybe not so surprisingly, actually you end up with 50. So 50 make it to the geosphere and 50 go up of one of these 3 waves. So, and then just to kind of finish out the balance, follow the energy. Okay, 12 units would go off perhaps into outer space. Okay, and again, 58 units to outer space from the atmosphere. It's just a possibility. It's just kind of showing you things that we've kind of talked about a little bit in some cases. Okay, so in this scenario, and I've done it before, I've kind of tried to check make sure their math is okay. Really, the 100 coming in is equal to the 100 going out, and that would be the geosphere and the atmosphere, back into outer space. So 100 coming.
So net 0.
Net 0, exactly. It's a wash. And actually, that leads us to the last topic. It's speaking of washes. Okay, I have.
Can you go back to
This one.
Sorry, I didn't see the bottom part. That word.
There you go. Balanced.
Okay, thank you.
You're welcome. Good. So there's this figure, and the last slide is actually a similar figure to show the same information. We talked, and actually related to your quiz question, okay, we talked, where is for the equinoxes, where's the hot spot on the Earth? You remember? Remember who's getting the most direct light in the equinoxes? Equators, very good. Yes. Okay. Perfect. Okay, who's getting the most direct light for the summer solstice? Tropic of Cancer. Yep, very good. 23.5 degrees north. How about December 21st, 22nd? Tropic of Capricorn. Perfect. Okay. So we know throughout the year we definitely have kind of this variation by latitude, right? That's latitude. But this is saying on a given year, for a given latitude, what is your annual budget? So this is how it works. And I had to, when I was getting ready to lecture, I kind of have to concentrate. Let me pull up the purple. So what you do is basically, let's pick on orange first. You see this orange line down here? Maybe I'll make it green. The orange line, I'm going to turn green. Okay, so here we go. This right here is energy that they receive at that particular latitude. So you see the bottom is the equator, the top is the pole. So can you see where they receive throughout the year, okay, more energy than anyone else, okay? So this is the most, and it kind of levels off. Okay. This other one, and I'll choose blue to kind of highlight the purple. This line down here, this outside line I'll pick at the poles, is actually the energy going out. Okay, so you see that actually they have the most energy going out in a given year, and these actually have the least amount of energy going out in a given year. Okay, so here at the equator they have less going out, they have more coming in. This little sliver here is kind of a pie sliver. Let's see, what color haven't I used? This little pie sliver right here then is the extra or surplus. Okay, in this case up here, this little pie sliver is the deficit or the amount they're lost. Okay, and the tipping point is just a little bit south of us. We're about 40. Go south a couple degrees, and actually there throughout the course of the year in general, the amount they have coming in is equal to the amount they have going out. Okay, so that's it. And this one actually says about the same thing. But instead of seeing kind of the way it was, if you look along the x-axis, it's latitude. So here between the 5 and the 5, actually that is the equator. And we have the northern hemisphere and the southern hemisphere, kind of the equator right here. Okay, so it's just another slide to say the same information. There about 38 degrees is this intersection right here. That'd be 38 degrees. So one more thing to say about this slide leading into Monday's topic. That's about 38 degrees. So here's the deal. You see those from the equator going out, it says energy transfer. One of the cool things, no pun intended, about things that are hot is basically they're just itching to give their energy to something that's cool. So yeah, just automatic. And I'll tell you that the oceans are great at, here we are. The oceans are great at relocating warm water, one way or the other. And actually, we're going to talk more about that next week. So relocating warm water towards the poles. But I'll pick on the United States. I'm going to ask you, and maybe you've dipped your toes in this ocean, the Atlantic Ocean, the Pacific Ocean. Okay, they are different temperatures. So I'm going to ask the Atlantic Ocean. How many people think it's warmer than the Pacific? You're right. And like I said, on next week we're going to talk about it's warmer because the way the water circulates is up this way. Okay, and a little cooler over there, the Pacific Ocean. Okay, that's because, and we'll talk more about this, the water circulates this way down the Atlantic Ocean. So yeah, I think that's
I
neat.
swam in the Atlantic, and then when I went to Oregon, I just rolled my pants up.
You swam here, but here you would just,
and after just a little bit, I mean, it was like completely red from the knees downward, but I had to go in.
Oh yeah, oh yeah, awesome, very good. Okay, so that's all I got for today, and so this homework due is due Monday.
Do you want our quizzes?
Oh, I do want your quizzes.